What's up, everyone? Welcome back. Patrick here. Moving on to another question dealing with transformations of quadratics. So what we have to do is we have to compare each set of graphs over here. So this one versus this one, then this one versus this one. And then we have to also describe the transformations on y is equal to x squared. So notice that all of these, well, almost all of these, this one is in a particular unique format, and we'll get to that. But all these other graphs, they are in the form y equals x minus h squared. Okay, and we've gone through a video of where we've described the transformations that are done with this h value. It basically takes the graph y equals x squared and it either shifts it left or right. So when I'm doing this, I'm assuming that you have watched those videos beforehand. So notice here, let's start with this one. We got y equals x plus 3 to the power of 2. So what is the h value in this case? Well, if you remember, what we do is we always switch the sign. So in this case, the h value is -3. Okay, if we plug in -3 over here, we got x minus -3, right? X minus that h value, which is the same as x plus 3. Okay, so you always switch the signs when you're dealing with the h value. Now, what does an h value of -3 mean? It means there is a shift or translation 3 units left, right? If the h value is negative, then the quadratic has been shifted by 3 units to the left. Okay, so if we were to graph that, if we take this and graph it, a couple of ways you could do it. So if we have x squared, which is like this, well, if we take this graph and we shift it 3 units to the left, let's pretend it's like over here, well, where is this new vertex going to be? Well, before the vertex was at 0 and 0, shifted 3 units to the left, so now this vertex here, this is going to be at an x value of -3, so we'll have -3 and 0. Just in general, if we have an x minus h squared graph, as we've gone through before, as I mentioned before, the vertex of that particular graph is always going to be at h and 0. So h is -3 in this case, -3 and 0. Now, if you want to make a graph that is a bit more precise, you can make a table of values. And what I recommend whenever you're making a table of values for a quadratic is always put the vertex in the middle so you could get a nice symmetrical quadratic. So notice the vertex in this case is -3 and 0, so we'll put -3 and that'll be 0. So what we would do is we would pick maybe 1 or 2 x values to the left of -3. So let's go -4, -5, and then we could go to the right, so it would be -2, -1. Right? And if you put the vertex in the middle, then what you'll notice is this y value will be the same, then this one and this one will be the same. Right? Because if you think about it, like at -4, you'll have a y value here, and then at -2, you'll have that same y value. So it should be symmetrical. The table should be symmetrical if you make a table with the vertex in the middle. So let's plug in -4 over here. So notice -4 plus 3, that gives us what? -1. -1 to the power 2 gives us +1. Same thing if you plug in -2. -2 plus 3 gives us +1. 1 to the power 2 gives us +1. What if you plug in -5 here? -5 plus 3 would give us -2. To the power 2 would give us 4. -1 plus 3 would give us +2. To the power 2 would also give us +4. So you can make a table of values like that if you want. And so when we graph it, then we'll have 1, 2, 3, 4. We'll have 1, 2, 3, 4, 5. Right? -1, -2, -3, -4, -5. So we start at -3 and 0. Then we'll have -2 and 1, -4 and 1, -5 and 4, which is up here, and then -1 and 4, which is up here. Right? And we end up getting a nice quadratic like that. Right? So if you want to make a precise graph or your teacher requires a precise graph with a table of values, highly recommend always trying to put the vertex in the middle if possible. Okay, so that's this graph. Now what about this graph? X minus 3 squared. What's going to happen then? Well, in that particular case, notice that here the h value is positive 3. Right? X minus h, x minus positive 3, that's the same as x minus 3 to the power 2. And if h is plus 3, well, if h is positive in general, what that does is it shifts the graph to the right. In this particular case, shifts 3 units right. Okay, so it takes this graph, shifted 3 units to the right. So just a quick rough drawing, if we got that x squared like this, right? If we shift this to the right by 3 units, it's going to be here now. Well, before the vertex was at 0 and 0, well, now this is going to be positive 3 and 0. And it's going to be like that. If you want to make a precise table of values for it, let's put the vertex in the middle. So we'll have 3 and 0, then pick 2 x values to the left. So 2 and 1, 4, and then to the right, 4 and 5. And so if you take these x values now, plug them into here, 1 minus 3 is negative 2 to the power 2 gives us 4. 2 minus 3 gives us negative 1 to the power 2 gives us positive 1. Here we got that y value of 0 already. 4 minus 3 gives us positive 1 to the power 2 gives us positive 1. 5 minus 3 gives us positive 2 in the bracket to the power 2 gives us 4. So again, nice and symmetrical. If we take that graph, we got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we're going up to 4. So 1, 2, 3, 4. So we'll have 3 and 0, 2 and 1, 4 and 1, 1 and 4, 5 and 4. We end up getting a graph like that, right? So this graph over here is the y equals x minus 3 to the power 2, right? So the difference is this one got shifted 3 units to the left, this one got shifted 3 units to the right. So let's go to part B now. Now, x minus 3 to the power 2, notice it's the same as this. So we just did all that work over here. But what about this graph here? This y equals 3 minus x. Let me give myself some room here. So we got 3 minus x to the power of 2. Notice how this one, it's sort of in a unique format. It's not in that x minus h squared format. Okay, but we can take this and put it in this format. And I'm going to show you how in a sec. But what I want to mention, just as a spoiler alert, is this graph and this graph, they're actually the exact same thing. Okay, and I'm going to show you algebraically how we can go from here to here in a second. But what I want to do with this particular function first is let's create a table of values and let's use the exact same x values over here. Because it's not in this format, it's hard to tell what the vertex is right now, but let's use this exact table of values and see what values we do get for the y. If they're the exact same, we should get the same y values, right? So let's see. So if we plug in 1 for x, 3 minus x gives us positive 2 to the power 2 gives us 4. 3 minus 2 gives us positive 1 to the power of 2 gives us positive 1. 3 minus 3 is 0 to the power of 2 gives us 0. 3 minus 4, negative 1 to the power of 2 gives us positive 1. Then 3 minus 5, negative 2 to the power of 2 gives us 4. And so notice that we are getting the exact same y values for these x values as over here. Okay, so we can be pretty confident that it's the same graph that we're dealing with. Because if you think about it, what's happening is that when we plug in 1 for this graph, we end up with negative 2 to the power of 2. But when we plug in 1 for this graph, we end up with 3 minus 1, which is positive 2 to the power 2. But because we're squaring these, this negative doesn't really matter. It's going to end up being a positive anyway. And then this is going to just be a positive as well. And so that power of 2, what's happening is even if you're getting a negative value here, and then a positive 1 here, or a negative 1 here and a positive 1 here, that's what's happening between these. When you're squaring it, you're ending up with the same y value. So that's the trick there. So this and this, they're actually the same graph. Now, the question is, how can we show that it's the same graph, not just with the table of values, but in a more precise way algebraically? Because if we can take this and convert it to this, then we for sure know that it's the same graph. Even with the table of values, we only use 5 points. We can't be like 100% sure, right? We could be pretty sure, but you never know. Maybe there's going to be some point that we don't know about, maybe in between all of these, where it's going to be different. So how can we algebraically show that these are the same? Now, what we can do is there's something called factoring that we're actually going to go through in a future section. But this 3 minus x, okay, what we could do is we could take out a negative 1 from it, and we could rewrite it as negative 3 plus x. And then this negative 3 plus x, we can rewrite as x minus 3. And then there's still that negative 1 in front, so it's like a negative over here. So this 3 minus x, we're just dealing with what's in the bracket, and this, they are the exact same thing. Okay? And you could test it. Like if we distribute the negative inside the bracket, what would we get? We'd get negative x plus 3, which is the same as 3 minus x, right? This is just, we could put the 3 in front, and we get that. Right? So if we distribute the negative, we end up with this. So this and this, they're the exact same thing. And again, we're going to go through a future section where we're actually factoring stuff out. There's going to be a process for that. But I just want you to know, or for you to see, confirm for yourself that this and this, they're the exact same thing. So what I'm going to do is I'm actually going to take this bracket here, the 3 minus x, and I'm going to rewrite it as that instead. Because they're the exact same thing, we can do that. Now, there's like a negative 1 in front here, right? So that's like a negative 1. We're multiplying by this. Now, when you're taking two terms, as a review, exponential rules, if you're taking two terms and multiplying them, and they're to the power of something, well, you could take each term to that same power. So that's what I'm going to do here, because notice the negative 1 and the x minus 3, we're multiplying those. So what we could do is we could take the negative 1 to the power 2, and then we could take the x minus 3 to the power 2. And then notice what happens. Negative 1 to the power 2 gives us positive 1. X minus 3 to the power 2 is just x minus 3 to the power 2. 1 times this is just that. So that's how you can algebraically show that this and this are the exact same thing. Right? It's just in a different format, so just be careful with this. And yeah, so this, because it's the same as this, it's the exact same transformations, we still have to describe them, shifts that base function y equals x squared 3 units right. Okay, so kind of a tricky question, kind of a unique scenario, but it does come up, so I wanted to go through it. Right, so these two graphs in part A are different, but then these two graphs in part B are the same.